Hello everybody, so we're going to start the second part of Unit 8, which is equilibrium. But before we get into what equilibrium is, I wanted to go over the learning target, which is I could describe what equilibrium is. So by the end of today, using chemistry words, you will know what equilibrium is, how it looks like on a graph. You will tell me how the molecules interact during an equilibrium reaction, and you will relate this to what you learned about reaction rates, the forward and the reverse reactions as well. Before we get into that, let's answer this question. What is equilibrium? So equilibrium doesn't mean that two things are equal to each other. It doesn't necessarily mean that. Equilibrium means that reactions go in two directions. One, reactions go in the forward direction, which is what I have taught you all of semester one. A plus B makes C, right? But in reality, reactions can actually go in both directions. A plus B makes C, but C could also go back to A and B. So it should look something like this. A plus B makes C, right? But in reality, C can go back and turn into B and A. For example, here in this picture right here, you guys see that there are water molecules in the liquid phase, right? All these water molecules eventually become a gas. They evaporate when the temperature is really hot, right? But what happens when you cool this? You put this beaker back in ice water. All of this gas right here is going to go back into the liquid phase. So when you heat it up, it goes into the gas phase, right? But when you cool the beaker down, it goes back into the liquid phase. So it's going in one direction and then it goes back into the other direction. And that's exactly what equilibrium is. Equilibrium is when you go from one direction to another and then you go back. So here, according to the definition, equilibrium is established when the rate of forward reaction equals to the rate of the reverse reaction. Okay, the rates are the same. Okay, therefore, while the reaction continues to occur, this means that the reaction does not stop at equilibrium. The reactions in both directions keep going on. The only difference is that the concentrations don't change, okay? It doesn't mean that the concentrations are the same. Like, oh, the concentration of A is 40 and the concentration of C must be 40. That's not true. The rate at which A plus B is turning into C is equal to the rate at which C decomposes back into B and A. Okay, that's what it means. That's what equilibrium is. Equilibrium just means that the products and reactants are undergoing at a constant rate. They're changing at a constant rate and the reaction does not stop. It keeps going. Okay? Just like in this beaker, water turns into gas, but then the gas could turn back into water. This is called an equilibrium reaction. Now, how do you actually put this into an equation? It looks something like this. Mercury oxide, which is a solid, can turn into mercury liquid and oxygen gas. However, the reaction can also go back into the opposite direction, so in the reverse direction, and form this again. So this is called an equilibrium symbol or an equilibrium arrow. Okay, this is how you would draw it. Down here, this is what you were usually exposed to during semester one. And just know that when there's an arrow that looks like this, the reaction is undergoing something called completion. It's irreversible, just like burning paper. You can't turn ash back into a paper. Therefore, that's considered a completion reaction. For example, you're lighting up a firework. You can't change the firework back into like the explosion back into a firework. You can't do that, right? You light up a firework, it explodes. You can't unexplode a firework. So that's considered a completion reaction. Okay, but up here we boil water, it turns into gas, but then you put that gas back into ice, it's going to turn into liquid again. Therefore, that's an equilibrium reaction. Okay, so know the difference. This is equilibrium, this is reversible, and this down here is not reversible. It's a completion reaction. Now, just to keep in mind, reactions do not stop when equilibrium is achieved, and just know that equilibrium means that the rate of the forward and reverse reaction are equal but still occurring, okay? A problem, one reason why I don't like the picture in the textbook is because it shows eight blue circles here and 8 purple circles here, and it doesn't mean that the concentration is going to be equal on both sides. It just means that the rate is going to be the same. So this reaction is in dynamic equilibrium because products are being converted to reactants and reactants are being converted to products at the same rate, okay? At the same rate, okay? At the same speed, okay? It doesn't necessarily mean that they're equal in concentration, okay? Just keep that in mind. So another example is this part right here, this graph. I love this graph because it shows that idea that I was talking about. Um, for example, right here, we can see that as the reaction proceeds, the concentration of NO2 is going to go up, 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 and then it reaches equilibrium. And then the concentration of N2O4 is going to go down, 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 and eventually it's going to reach equilibrium. Are the concentrations the same? No. But if you look at the right side and we actually analyze the rate right here, the rate of NO2 is going to go up and eventually stabilizes. The rate of N2O4 is going to go down and eventually it stabilizes. Is the rate the same? Yes, the rate is going to be the same. The concentration on the left side is not. So just keep that in mind. Equilibrium is when the rate of the forward and the reverse reaction are the same, just like it's shown here. It doesn't mean that the concentration is going to be the same. Okay, so that's why I love these graphs, because it shows that difference. Clearly shows that difference. And the last thing I wanted to talk about is something called Le Chatlier Principle. Now that you have a reaction that's at equilibrium, if a reaction is disturbed by a change in temperature, pressure, or concentration, the system, the equilibrium reaction, will shift in a certain direction to counteract the effect of the disturbance or stress. Okay, so that's like, whoa, I don't understand what I just read. It basically means that if there's a reaction that's at equilibrium and you disturb it somehow, it's going to change. Okay, the equilibrium reaction is going to change. For example, it summarizes it in that red, in the red wording of this slide. If equilibriums are disturbed, the reaction will respond. Okay, to make more sense out of this, um, let me give you an example. Okay, if you at home you hang a coat hanger by a rubber band, you create a system that is in equilibrium. Okay, the force of gravity will pull the hanger downward and is exactly balanced by the rubber band trying to pull the hanger upward. Now take a second coat hanger, okay? Hook it onto the same rubber band, and the extra weight is going to be a stress, some disturbance that is applied to that system, okay? Stress is another word for something that causes a change, okay? The equilibrium is disturbed by the stress and the rubber band starts to lengthen. However, the system soon reaches a new equilibrium. Okay, so this man named Henry Le Chatelier, his picture is shown right there. He is the one who studied the way in which chemical equilibrium responds. Okay, and his findings are known as Le Chatelier Principle. The principle again states that when a system at equilibrium is disturbed, the system adjusts itself to reduce that change. Okay, it responds. Okay, for example, if you are disturbed by a loud noise, you're going to move into a quieter place. You're responding. Okay, so Le Chatelier principle just says how are chemical reactions going to respond if there's a change in concentration, pressure, and temperature. Okay, so that's the main idea. How do concentration, pressure, and temperature impact equilibrium? Well, let's look at the first one, concentration. If we add more of a product or a reactant, then our reaction will shift to the other side to compensate for this amount. That probably made absolutely no sense to you, and that is why we come up with examples. So I have the following chemical reaction. H2 turns into H3O and OH, and then it's reversible, right? If I add more product, so you're adding more H3O, okay, you're adding more of this H3O right here, then my reaction will shift to the right or to the left. Okay, since you're adding more here, since you're adding more product, the reaction is going to shift to the left to counter this change. So, oh shoot, there's too much product. We need to cause that to stabilize. We need to cause this reaction to stabilize. So what we're going to do is we're going to make more water to stabilize this change, okay? So the reaction is going to shift to the left, okay? So your answer will be to the left. Again, you have too much product, it must go to the left. If you added water, you're going to have too much water, so the reaction is going to go to the right, okay? So again, the Chatlier principle just says the reaction is going to shift to counteract that stress, that first change that happened. Okay. Here's another example. Pause it after I'm done. Reading it. I have the following equilibrium. Calcium carbonate turns into calcium oxide and carbon dioxide. If I add calcium carbonate, so you're adding more of this right here, then will my reaction shift to the right or the left? So you're adding more and more and more reactants. Where is the reaction going to shift? To the right or to the left? So go ahead and pause this, answer it first in your head, and then press play to see what the answer is. So again, if you add more reactants, the reaction is going to proceed to the right side because you want to counteract this change, okay? So your answer is to the right. Oh, I have too much of this. I need to shift the equilibrium reaction to the right to counteract that first change. The second thing is pressure. If we increase the pressure, the reaction will shift to the side with less molecules. If we decrease the pressure, the reaction is going to shift to the side with more particles. Okay, so just keep that in mind. The more pressure, the more the particles move. But if we want to counteract that change, we need to shift the reaction to the side where there's less molecules, so we can make more of those molecules to counteract that change. Okay, so that's the concept behind this. So here we go. I have the following equilibrium reaction. There's 1 mole here and there's 3. So on the left side we have 4 moles total, okay? So let's write this down. We have 4 moles on the left side. And on the right there's only 2 moles. 2 moles of stuff, okay? So if there's more molecules on the left side and I increase the pressure, then will my reaction shift to the right or to the left? So take a look at your notes and then press play to see what the answer is. Okay. So again, if I increase the pressure, it's going to move in the direction where there's less molecules. Therefore, this is the side with less molecules, so it's going to shift to the right. Okay, so here's the next problem. There's 4 moles on the left. Okay, so there's 4 moles on the left, and there are 2 moles. 2 moles on the right. Okay, if I increase the pressure, then will my reaction shift to the right or left? So increasing the pressure moves in the direction where there's less molecules. So there's less molecules on the right side, so there's going to be a shift to the right. So there's a shift to the right. Okay. And the last thing is temperature, and we'll get into that next week. okay? So don't worry about temperature, we'll get into that next week. Go ahead and write your notes down.